Hello, everyone, and thank you for attending today's webinar, Characterizing Glass Fragments Using Micro-XRF Intensity Ratios. Before we begin, I want to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget at the bottom and submit your question. We'll try to answer these at the end of the presentation, but if a fuller answer is needed or we run out of time, it'll be answered later via email. We do capture all questions. A copy of today's slide deck is available in the resource list widget that looks like a green folder at the bottom of your screen. You can expand your slide area by clicking on the Maximize icon on the top right of the slide area or by dragging the bottom right corner of the slide area. If you have any technical difficulties, please click on the Help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webcast will be available approximately 1 day after the webcast and can be accessed using the same audience link that was sent to you earlier. Now I'd like to introduce today's presenter. Andrew Lee is a Senior Applications Engineer at EDAX based in Mahwah, New Jersey. Prior to joining EDAX, Andrew attained a Bachelor of Science in Materials Engineering at Rutgers University in May 2006. Shortly thereafter, he joined the EDAX as the XRF Applications Engineer and in 2013 became a Senior Applications Engineer. His primary duties at EDAX include providing applications and sales support for the Orbis Micro-XRF and SMX-XRF products. When he's not in the office, Andrew is also involved in supporting these products at trade shows and EDAX workshops around the country. He finds these regional workshops to be particularly rewarding as they offer a direct collaboration between sales and applications to increase exposure for EDAX products in underdeveloped territories and markets. So now over to you, Andrew, for the presentation.
Okay, thank you, Sue, for the intro. Thank you, everybody, for joining us for today's EDAX webinar. My name is Andrew Lee, the XRF Applications Engineer. And the topic I wanted to discuss today was characterizing glass fragments using micro-XRF intensity ratios. So the webinar for today is going to discuss an alternate method for quantifying and characterizing small glass fragments as are typically performed when analyzing in the context of criminal forensics. When measuring very small glass fragments, there are various analytical challenges, and with the higher scrutiny required for potential use as evidence in court, a more defined method was created in ASTM E2926 by a group of forensic analysts. So this is likely to be a relatively familiar topic for those who are in the field of criminal forensics, which today seems to be a relatively large portion of the people who are joining us. But for those who are not in criminal forensics, one can imagine that from perhaps a breaking and entering scene or a hit and run scene, for instance, broken glass can be recovered from the scene, which will be used as evidence. And they can come in a variety, an assortment of sizes and thicknesses and shapes, ranging from the micron level and anywhere greater. So with, of course, the preference to keep these samples intact and minimize any kind of sample preparation, micro-XRF is a technique which lends itself quite well to analyze these samples as is. However, with such a variety of sample dimensions and shapes, as we mentioned, there also comes some hurdles with interpreting the spectral data from these types of samples. So some common issues and common things that have been discussed in this context are beam overspill, and also the effect of variation in sample thickness and topography, which again will impact the quantitative data. Conventional XRF quantitative routines, such as fundamental parameters, makes assumptions regarding the sample and makes the assumption that it is infinitely thick with respect to the X-ray response. And making that assumption on small glass fragments can lead to mischaracterization. Also, it's necessary to establish a definition for acceptable ranges for inter and intra-laboratory comparisons to establish what can be defined as coming from the same composition or what would be different. So as mentioned, Micro-XRF is a favorable technique for measuring these samples. It is non-destructive in its measuring technique. So the glass fragments, regardless of their shape and size, can be analyzed without any destruction, and they could also be loaded into the sample chamber with relatively minimal or no sample preparation. So the sample is measured as is, which is favorable for this type of application. Also, in comparison to some other techniques such as CPMS, as I mentioned, is non-destructive, so the sample can be recovered. And in comparison also with SEM EDS, we have more favorable sensitivity for elements that are more typical when analyzing trace elements in glass, which typically tend to be elements with higher atomic number. So we here have some example detection limits for various elements in a soda-lime glass. And you can see that we typically will achieve below 100 parts per million, well below 100 parts per million for most elements. And as the atomic number increases, you notice the sensitivity actually improves, which is in contrast with EDS, where the sensitivity actually is more favorable for the lighter elements. So while we are mostly familiar with the benefits of Micro-XRF, and these are advantages that are relatively universal for the technique, as mentioned, there are still some hurdles and some issues when interpreting the spectral data when it comes from such a variety of sample shapes and sizes. These are issues that would typically not be present if the samples were all uniform in thickness and shape, or if they were all bulk thickness. So to now review some of these issues in more detail, the first one we have is the effect of sample size. The effect of sample size is quite apparent, and it becomes a bigger factor if the samples are substantially smaller than the actual excitation area provided by the X-ray beam. So this the excess excitation area is referred to as beam overspill and can cause additional background noise with polycapillary optics, which have a beam diameter of 30 microns at Moly K full with half max for the Orbis PC. This issue can be minimized since the nature of having a smaller beam diameter. But as the beam diameter increases, more typical with a monocapillary, which can go up to 300 micrometers in diameter, this effect might become more significant. So the background noise should obviously be minimized by selecting the most ideal sample size relative to your beam diameter, and also elevating the stage above the sample, which is a common sample loading technique with Micro-XRF, which is to take the sample and put it on some kind of substrate or adhesive, which is undetectable with XRF, and elevate it above the stage to minimize scattered X-rays that come off the stage. So in this example slide, we have an overlay of two spectra, basically exhibiting the effect from the last slide, where we have a 300 micron monocapillary beam and analyzed a particle that's 300 by 300 microns, which is pretty much no beam overspill, versus a particle that's 100 by 50 microns, which has a substantial amount of beam overspill. You could see the significant increase in background noise when you have such a great amount of beam overspill. The next influence is from sample thickness, and sample thickness plays more of a role, not so much in the background, but more also the actual direct elemental count rates. Bulk thickness, which is or also known as saturation depth, would be the minimum thickness where roughly 90% or above of the incoming X-rays are absorbed by the sample. The values sometimes varies depending on the source. I've seen 90% absorption, 95 or 99%. But the main takeaway from that is that the X-ray response at that point is nonlinear as it starts to approach saturation. So in the graph down here, the bulk thickness would be more towards the right-hand side of the graph, where the intensity ratio is approaching 1, versus having a thin sample, which would be more typical with glass samples that you might get within from a crime scene, for instance, where you have sample thickness which is not considered to be bulk thickness. And in that case, you have signal response, which is linear. So the thickness versus intensity follows a linear relationship, where the intensity increases relatively in a linear response with the thickness of the sample. So you have two different instances. Typically with traditional XRF quantitative routines, as I mentioned, you have mainly fundamental parameters, which assumes that the sample is bulk thickness. But since we have samples which are not actually bulk thickness, their intensities will vary, and based on the variations in intensities, using fundamental parameters is obviously not the most appropriate routine to use, because it will not, the quantitative routines will not reflect the influence of the sample thickness. So the next slide just has another example of the influence of sample thickness, again on a iron particle, one which was a bulk particle, infinitely thick in the darker spectrum, and then that analyzed and overlaid against a thin plated steel particle, which is in green. And they are both normalized to the iron peak, which is the main element. And normally, just looking at the spectra, since they are normalized, they might look very similar. But actually, if you look at some of the other elements, like in this case moly, you could definitely see a change in relative intensities. They are not equal, and if you were to quantify this sample, of course, you would get two different answers, even though they are of the same composition. So in this graph, we have various sample matrix types and plotting their analysis depth relative to the energy of the analyte photon. So basically, if we want to focus on the matrix of interest here, which would be closest one would be SiO2 in purple, that line shows us that as we increase the energy of the analyte photon, the actual analysis depth goes to quite a high number. We at, for instance, 10 keV have a analysis depth of roughly 1 millimeter. So that's relatively thick, and certainly much thicker than what you would typically get for glass particles. As we start to fill in some elements into this graph, for instance, using iron K lines, and then on the higher end we have cadmium K lines, we could see where those correlate with their respective thicknesses. So if we are, for instance, analyzing an element such as iron in a glass, we have an analysis depth somewhere at maybe a couple hundred microns nominally. And if we analyze a higher energy line, something like in the range of cadmium, we have analysis depth exceeding 1 millimeter. So the range can vary a large amount depending on the energy of the analyte element and the actual matrix of the sample. So in this case, we could clearly see that if we were to get a glass sample that's in the range of in the microns to millimeter scale, we're still not approaching bulk thickness, and we can still see the effect of sample thickness in that case. And that last animation was for the cadmium L line, which is on the lower end. So the general approach to characterizing samples which exhibit the influence of sample thickness and size and background noise would be to employ internal ratios as opposed to the traditional fundamental parameters quantitative routine, which gives you weight fractions. Again, it assumes samples are homogeneous and bulk thickness. So again, we've seen why that these samples would not be appropriate for that kind of routine. So we switched to a different method. The idea here being that internal ratios are not actually calculating weight percents. You're actually using the element of the intensity of one element in that sample, and you're ratioing that against another different element within that same sample. So that's why it's called internal ratios, because we're ratioing the element intensity to another element that comes from the same sample. And this should compensate for majority of the sampling effects within a single laboratory setting. So again, this would be more acceptable because it actually compensates for a lot of these effects, as opposed to using weight fractions, which we would not know if it came from a bulk sample or a thin film sample, and the quant results would not be accurate. So it would not be acceptable for use, obviously, in court or as evidence. We would want something that takes into account the influence of all the physical aspects of the sample. So using internal ratios is the general idea. We can see in the next slide an example of the benefit of using internal ratios. This example shows two plots. The one on the left are just the raw net intensities of various soda-lime glass standards of various thickness and different levels of calcium. So as we plot them, the intensities versus the thickness is very scattered, and it does not have a very good correlation. Then if you actually normalize those calcium intensities against the internal silicon intensities, which is just the silicon intensity from that same sample, and you ratio all those calcium intensities and then replot them, you get a much better correlation. for the different thickness of the samples. So we get a much more better correlation and still compensate for the effect of sample thickness. Okay, so that is the general idea. The quantitative routine of using internal ratios has been in XRF software for quite a bit, but the actual procedure now outlining how to use these intensity ratios to specifically characterize these glass fragments and also to determine if they share the same composition or not. Now this comes from the ASTM method, E2926, and this gives a much more specific outline as to how to approach this. So the next series of slides will illustrate this procedure using some examples from bottle glass fragments. The procedure was, of course, written to be used in the context of criminal forensics. Using bottle glass fragments is still soda lime glass and relatively close in composition to glasses that might be seen in practical setting. So it will be used as an example to illustrate the steps in this process. It will involve acquiring multi-point acquisition of the samples to attain raw intensities, and it will also require normalizing with a calibration standard like SRM 1831, which is a glass standard, and that step is to help for future interlaboratory comparisons with wanting to maybe build a library or compare results from a particular glass with another lab, which might have a different instrument configuration. So using the SRM 1831 can help standardize those results. And then we would then calculate the internal ratios for each sample, calculate the average ratios and their standard deviations. And as defined in the method, the acceptance ranges can be defined as plus or minus, the average plus or minus 3 times the standard deviation. And if the average intensity ratios of the unknown fall within that range of the known, they could be defined as having the same composition, or if it falls outside that range, they could be concluded as having different composition. So in this example, for now we'll just leave the identity of the glasses just labeled as A, B, and C, but 3 different soft drink glass bottles were selected, and they had varying dates of manufacture, different companies. They were individually shattered, and fragments were selected from samples A, B, and C, ranging from 0.5 millimeter to 2 millimeters in length. They were cleaned with isopropanol. So from each of the 3 glass bottles, 2 fragments were selected from 2 small fragments were selected from each bottle, and 3 points were analyzed on each fragment. And of course, the flattest, smoothest portion of the sample was selected. Of course, it was not perfectly flat, but you could choose the best part that's exposed. And the fragments were adhered to double-sided carbon tape and elevated above the stage as usual using a simple sample cup, and that was again to minimize stage scattering. So that leaves us with a total of 6 points for each glass bottle. And this slide is just to give us a visual. We have samples A fragment 1 and A fragment 2 in the first column, and then fragment B1 and B2 and C1 and C2. Basically, the point here is that while the samples were not microscopically small, we could still handle them with tweezers, and they were still visible with the eye. The beam overspill is quite eliminated in this instance because we're using a 30-micron polycapillary, so beam overspill is not an issue. But since the samples are no more than maybe a millimeter thick, we still have the influence of sample thickness, as we saw. So although the samples look relatively large and certainly big enough for a 30-micron polycapillary to get stable spectral data, in actual fact, they are not thick enough to get results like that. They will the intensities will vary based on their thickness, because as we saw in the earlier slide, depending on the element that you're interested in, even 1 millimeter is still not thick enough for a soda lime glass. And of course, just to prove that point, I do have an overlay of those of the spectral data from those 6 samples coming up. Just to quickly go over some acquisition conditions: 48 kV, 500 microamps on the tube, basically as outlined in the ASTM guide, just to not exceed excessively high dead time. So dead time is kept at about 30%. Acquisition time was kept at 1200 live seconds, as was most of the spectra in the guide or in the ASTM method. And then we used the 30-micron polycapillary, and all samples were run in vacuum. So after running the auto run, which collected all the raw data from all of the glass samples, we then have to identify the elements of interest, and then one step further, determine which of those elements we would want to use for quantification. That also is defined in the method for elements that want to be labeled in the spectrum. They must have a signal-to-noise ratio in excess of 3. And then to use those elements for quantification in this intensity ratio and process, they have to have a signal-to-noise ratio greater than 10, where the signal-to-noise ratio is equal to the net intensity ratioed against the noise, and the noise is equal to the square root of the background intensity. So using those requirements, actually in this particular scenario, magnesium was excluded from the quant. It did not satisfy these conditions. It did not have a sufficient peak to background or signal to noise ratio, and so instead we chose chrome as a potential replacement for the ratio where magnesium would be used. So in this spectral overlay, this is the overlay between all 6 glass samples. So I basically just took a representative spectrum from each of the glass samples on each of the 6 glass samples, and I overlaid them. And although you may not be able to see the finer lines, you can clearly see that the intensities and the peak heights and the background levels for the 6 spectra are not consistent. You can clearly see variation in, for instance, the iron, variation in titanium, chrome. Background level is different for, substantially different for one of the spectra. So just looking at the qualitative data, we cannot really determine with such a variation in sample size and thickness whether this is really due to actual variation in composition, or if this is just due to the influence of the the actual sample dimensions. There's no actual clear indicator whether we can eliminate one as being clearly different. They're all relatively close, but still obviously different enough where some ambiguity is still there. So that would, in my mind, qualify to then take this one step further and actually use the quantitative procedure in the guideline, because as the guideline states, if these qualitative data, if the overlay showed samples that had vastly and clearly different compositions, just visible from a peak overlay, you could make a conclusion that they are different composition. But when they're relatively close and still a bit ambiguous as they are in this case, you would then want to take it and actually do the quantitative routine for these samples. So obviously not good for FP-based quant. These samples would probably not give you a consistent answer or a reliable answer as to whether they are of the same composition or not. So having now the raw data for all 6 samples, one kind of step that we take in the middle is to normalize the intensities to their respective elemental intensities from SRM 1831, which I mentioned is used as sort of a standard to normalize the results so that interlaboratory comparisons can be made. Various labs might have different instrument configurations. Even if you have 2 Orbises at 2 different labs, they could have 2 different hardware configurations. And in those instances, you cannot make a direct spectral you cannot make a direct comparison of the quantitative data, because again, even the configuration will affect the X-ray intensities. So to get some normalization, the SRM 1831 is used. 3 points are collected off of the infinitely thick plate, the bulk SRM 1831 standard. Those 3 points are averaged, and so the elemental intensities were taken as an average of the 3 points. And then that averaged intensity was used to normalize the respective elements in the raw data from the unknown samples. So just to give an idea for one sample, not to crunch too many numbers on the slides here, but on the top you have the raw intensities for all the elements, many of which were, by the way, not used. Of course, as I mentioned, we eliminated magnesium, so forth. Then we have the SRM 1831 averaged intensities for those respective elements. And then now you have the normalized intensities for the original data set from the 6 unknown samples. So once you've actually normalized those values, you can then take that and use that for future comparison among other labs. Of course, if comparisons were going to be kept exclusively to just one single laboratory setting, perhaps this might not be required, but I just took that step anyway. And then after those results have been normalized, we can calculate their intensity ratios or their internal ratios. These ratios are defined in the ASTM method, and most of them work out very well, but in some instances, as I mentioned in my particular case with magnesium, that was taken out because it did not satisfy sufficient signal to noise. So in that instance, I replaced it and used a chrome ratioed against iron. The reasoning for that was that they are they're very close to each other in atomic number, which generally makes them good for ratioing, as it minimizes takeoff effects, which is more substantial as the atomic number spreads between the two elements. So in this case, chrome and iron was used, but all the other ratios were taken from the method, and they were then ratioed from all the 6 points to get one average ratio for each, and then their standard deviations were calculated, and then the average plus 3 standard deviations and the average minus 3 standard deviations were created. And then from here, the comparisons can be made between the various glass samples. Of course, if they fall within the plus or minus 3s, then they could be concluded as being the same. And if it falls outside, then they can be concluded as not having the same composition. So in this case, as I mentioned before, we have 3 glass bottles, and we have 2 fragments from each bottle. So that allowed me to make comparisons within, to make comparisons from 2 fragments from the same bottle, and then to make comparisons between fragments from different bottles. In this slide, I have all the comparisons between fragment 1 and fragment 2 from sample A, sample B, and sample C. Now, to kind of best illustrate all of this data, I just opted to make some graphs where the blue and the green bars on the left-hand and right-hand side are the plus and minus 3s from the average, and then the middle red bar is the average intensity ratio for fragment 2, which is in this case going to be made the unknown. And then the ratios, actually the ratios correlate in order with the ratios in the last table. So all the ratios that we see here have been plotted in the same order in the next slide. And basically between samples A, B, and C, we see that in each case, fragment 2 always falls within the ranges set by fragment 1. So it confirms that, yes, they have the same composition, which is something that we already knew, and it successfully confirms. And then now to compare fragments from different bottles with each other. The first instance, I'm comparing bottle A and bottle B. So in this case, when I actually create those ranges, the plus and minus 3s for sample A, and then I use the average ratios from sample B to compare, a number of the ratios actually fall out of the range. So immediately we could see that the ratio for calcium to potassium and the calcium to iron, strontium to zirconium, and the chrome to iron, they all fall out of range. So that's definitely not ambiguous, and we can conclude that A and B do not share the same composition. Then I compared A with C, and we actually see we use the ranges set by sample A, and we use the average ratios from sample C, and they all fall within the acceptable tolerance range, and can be concluded that sample A and C share the same composition. And of course, if sample A and B are different and sample A and C are the same, then we could then conclude that sample B and C are going to be different. And when we compare B and C, yes, we see Once again, that a number of the ratios fall out of range when we compare the ratios for sample C against the ranges set by sample B. The ratios for calcium to potassium, calcium to iron, strontium to zirconium, and iron to zirconium all fall out of range. So that confirms for us that sample B and C are in fact different composition. And in fact, this makes sense because the glass bottles, as they now can be identified, have been basically sample A is a Coca-Cola bottle, sample B is a Pepsi bottle, and sample C is another Coca-Cola bottle. Two Coca-Cola bottles were manufactured during different dates, but have the same country of origin, same brand, same composition, and of course, sample B, Pepsi bottle, was a different composition than the other two. So during this process, there are also other factors to take note as well. When you look at your raw spectral results, the actual spectral data, it's important to look for peak overlaps and any interference with spectral artifacts, which can obviously influence your intensities. And there are some software methods to process out some of the spectral artifacts. And of course, the software does its best to deconvolute overlapping peaks. But again, it would be good to perhaps maybe process and delete the escape peak, for instance, if it overlaps with an element of interest. Of course, exclude elements with insufficient signal to noise. As saw here, I excluded magnesium because it did not qualify based on the requirement for having signal to noise ratio of greater than 10. Presumably that would lead to poor statistics with regards to the intensity ratios and might lead to mischaracterization of the samples. And if an element is going to be removed from the intensity ratio for maybe an insufficient signal to noise, then it's important to select a replacement element and select a ratio where the elements have atomic numbers that are relatively close to each other to reduce the effective takeoff angle. And of course, to ideally choose the smoothest and flattest portion of the sample. So in closing, that concludes my example for this ASTM E2926 method. So just as a closing summary, the internal ratios, which is a quantitative method where you use one element intensity and ratio it against another element in that same sample, it actually accounts for much of the physical sampling effects, such as variation in sample thickness and sample size, particularly for glass particles in criminal forensics, where just by nature of the samples, these glass fragments will vary greatly in size from microns and above. The FP fundamental parameter-based quants obviously can mischaracterize these samples because they make the assumption that it comes from a bulk thickness sample and does not make compensation for variation in thickness. So this procedure in the ASTM guide outlines a more specific method developed and adopted among forensic labs used to normalize intensity ratios and create defined statistical ranges to determine whether glass actually comes from the same composition or not. And utilizing this method on the three example bottle glasses in this particular case study showed correlations between two samples which came from the same Coca-Cola company and showed difference in composition with the Pepsi bottle. Okay, so that concludes the slides and the webinar. So thank you again for having joined us, and at the moment I'll take some questions. I don't think there's, oh, here's the Q&A, okay. So yes, if you have any questions, you could type them through the Q&A box. Right now I have a couple. Just will. So one would be, is this needed for every situation in bulk samples? So as I mentioned before, if the sample, regardless of its thickness, if the sample is, if you take the spectral data from the samples and it's evident in the actual spectral data, you can make the quick decision on the spot just from qualitative data that they are different composition, whether it's maybe because there's one element that's clearly not in one sample and is clearly present in the second sample, then that could be a distinguishing element. But in other cases, when there are differences, but the differences are not substantial, or there's still some ambiguity, I believe that this method needs to be employed in those situations. Second question, why were the tolerance ranges so big in the graph? Well, that could come from a number of reasons. A lack of precision would be my first answer. I measured 3 points, 3 random points on a sample which did not have consistent thickness. And as I said, maybe other elements were a little bit too close to the signal-to-noise threshold required for quantifying these elements. But yeah, I believe some have better statistical ranges just because you have better precision for those elements. Yeah. Why 48 kV for the acquisition conditions? 48 kV is just a number that I've got into a habit of using, but basically the main requirement would just be to use a kV that's high enough to excite the, even the highest elements that you would potentially be interested in, which I'm assuming would probably be strontium or zirconium. So yeah, in that case, you want to just use the overvoltage formula, which is about 2 to 2.5 times your highest element of interest. I could have used 45. I just used 48 because it represents 95% tube power. I just got that in my head. So no particular reason. You could have used 45. You could have used 40. Let's see. Another question is, do you have to proceed with quantification of the elements, or is it okay if the elements are present or not? I believe that might be that answer might be found in the signal-to-noise requirement. If the peak that you suspect is there exceeds a signal-to-noise ratio of 3, you could label it, but you unless it exceeds a signal-to-noise ratio of 10, it's recommended that you don't use it. So no, you would not have to proceed with quantification of that element just because it's listed. If it does not satisfy the signal-to-noise ratio, I am under the understanding that it can be excluded and not used. And the effect of roughness on measurement errors is another question. So what about roughness effect on measurement errors? And of course, this is also an effect of samples that might not be perfectly flat or might have roughness to the topography. Micro-XRF is a bit less sensitive to these effects than, for instance, ASTM EDS, especially with the bigger the beam, the less heavy this influence might be on your results. But also the ratios that we select for the elements are ideally chosen again in close atomic numbers, so the elements that you ratio shouldn't be too far apart in atomic number, and that could also reduce the effective takeoff angle as well. And why did I, and the last question I'll answer is, why did I use bottles and not window glass? Good question, just accessibility, and yeah, just wanted to make sure we had some quick accessible glasses that we knew would be different composition to illustrate this case. But yeah, we could have used window glass for sure. I think the comment here was that you ratio magnesium because you usually see magnesium there, but not commonly seen in bottle glass. So that comment makes sense. Obviously, that was the reason we excluded it from the quantification process here, was because we didn't see it, and I guess the expert says no magnesium in bottle glass. So that makes sense, yes. Okay, so that was the last question. That wraps up our Q&A session. Thank you again for joining us, and that wraps up our webinar session. Thank you.